Hi, good morning, everyone. I'm Behrad Babaee. I'm a technology evangelist in Aerospike, a database company. Can everybody hear me? Cool. So I started my software engineering career as an embedded system developer. Embedded systems are very sensitive to efficiency, so I was trying to build efficient applications, and I want to talk about efficiency in this talk. So to give you an idea, when you have a CPU, imagine the CPU can do, for example, 40 units of instructions per second. If you write an application that the main task that it does takes 5 units of transactions, it means that you can do 8 tasks per second on that CPU, and the speed of each task is going to be 1/8 of a second. So if you want to do more, there's no other way than reducing the number of the instructions that your main task requires. So basically, you have to reduce the number of instructions, let's say, from 5 to 4. So if you do something like that, then you would be able to increase the throughput from 8 tasks to 10 tasks, and you can increase the speed from 1/8 of a second to 1/10 of a second. So very early on in my career, I understood that by increasing efficiency, I can increase the speed and throughput of my applications. But you know, at the beginning of the millennium, around year 2000, there were only a handful of internet companies that really needed to deal with the scale of the internet. But by the end of the 2010, you know, the end of the first decade, almost every company had to deal with massive scale of applications. Everybody wanted to do more. But we have a few problems back then. So traditionally, there were a few ways to make applications go faster. One of them was, you know, Moore's law. Every 2 years, our applications were getting twice faster, right? The frequency of our CPUs were getting twice every couple of years. But that stopped, right? Around year 2003, 2004, CPUs didn't have that frequency increase that we used to get every 2 years. So we couldn't increase the speed of our application, the throughput of our application, by improvements in the hardware. Then there were algorithms. So we were always trying to use better algorithms, better data structures to improve the speed of our applications. But the truth is that most of these algorithms, most of these data structures were invented in 70s and 60s. By 2010, we were already using almost all of these good algorithms. And yet there are still new algorithms coming in, but they are not improving anything by 10 times that we can deal with the scale of internet. So we switched basically to a scalability, right? So of course, the scalability existed even before that, but around 2000, around year 2005 to 2010, scalability started to become significantly more important than efficiency. And when we were adding these, when we were making these applications that we had scalable, we of course added some overheads, right? So it wasn't as efficient that it used to be. But the good thing about the scalable applications were that you didn't have just one CPU now. You could have as many CPUs as you wanted. So for example, if you wanted to do that task 40 times per second, you could increase the number of CPUs to 10, and then the throughput of your application could have been increased to 40 tasks per second. Something that we couldn't do before. There wasn't any way to make our application work with just one instruction. So scalability became the new way to increase the throughput of our applications. And scalability can improve speed, but you have to define speed here. If you're talking about how fast I can do 40 tasks per second, yeah, scalability can help. Because if you add 10 CPUs, you can do it in 1 second. If you do it with 40 CPUs, you can do it in half a second. So it can definitely improve the speed. But if you're talking about the amount of time that one task takes, usually scalability reduces the speed, right? Because you have to add a few cycles to make the application scalable. So, but yeah, by increasing scalability, we could increase throughput. And at the time, we started to have all of these scalable applications, the scalable technologies that everybody's trying to use. And as I was a performance junkie, I started using all of them. I wrote my first MapReduce job in 2009, and then I continued with HBase and HDFS and Spark, and then, I don't know, I had a stint with MongoDB and Couchbase, and then eventually I started working with Cassandra. Cassandra was a very, very fast database, and I really liked it. Other than being fast, it was ridiculously scalable, right? You could easily add more servers and, scale the application and scale its throughput. And because of that, I was thinking that Cassandra is the most performant database that you can find. The extent of the affair got to the point that I started working for the main contributor of the Apache Cassandra project company. So I joined the company, and I was working there for a number of years. Till last year, no. Where did we go? This is not working. What? Okay, sorry. Till last year, I heard about this company, Aerospike. And I started looking at their claims, and I found out that their claims basically doesn't make any sense to me. They were saying that their database is 5 times faster, and it uses 5 times less resources than what I knew. And I could imagine that an application can be 5 times faster, but I was always assuming that it should be with 5 times more resources, right? So it didn't make any sense that why they are this much faster and they are using fewer resources. So I thought that, okay, I need to test this to find out that if this is actually true. So I did some tests, and surprisingly, I found out that all of those claims are true. They can, handle 5 times of the throughput with 5 times speed on 5 times less resources. So, yeah, these are a little bit spoiled now, but I did the right thing that every smart person should do when they face the defeat. So after I joining Aerospike, I started to looking for this, that how is that possible, that they can run 5 times faster on 5 times fewer resources? And I found out that, I already knew why this is happening. Because imagine that I want to do 40 tasks per second, right? So if my goal is to do 40 tasks per second, and I'm doing it, let's say, on 10 CPUs, if I somehow can improve the performance of the application by 5 times, so each task take 5 times less number of instructions to run, that application is going to need basically 5 times less resources, right? Ah, come on. This clicker is... Yeah, so you need 5 times less resources, right? So I can basically run faster and run on 5 times less resources. Basically in computers, because the clock of the CPU is always the same, whenever you increase the speed of the application, it literally means that you need less resources. This should be basically very, very basic. You should understand that. So I understood that efficiency can improve the throughput, can increase the speed, and also you can do it on lower resources. So efficiency can also reduce the amount of resources as well. And then, resources have a cost, right? If you use AWS so far, you know that there's a price attached to something. So if you can reduce the amount of resources by 5 times, you can reduce the amount of costs that you're spending on AWS by 5 times as well. So I thought that, okay, that's really good. Again, this is not working. But now you should be asking this from me, that I just told you that the CPUs are not getting any faster, right? And we don't have any new data structures, and we don't have new algorithms. So how come Aerospike can run 5 times faster? So I have another talk tomorrow. It's at noon in Data Engineering Theater. So if you're interested to know how Aerospike runs 5 times faster, please join that. You're possibly going to enjoy that talk as well. But now to the main topic of this presentation. So a few months ago, I guess it was around March or April, I read this article in Bloomberg that was discussing about the emissions of software industry. So there was a paragraph in this article that I suggest you to have a look if you're interested in these kind of things. It says that by 2030, it is expected that the IT industry uses to use 20% of the energy of the world. 20% of the energy in the world will be used by IT systems. This was mind-blowing, right? This is literally mind-blowing because so far, until then, I didn't know IT industry can be this much polluting, right? You know, energy is the main source of producing CO2 emissions. So I started to think that oh, this is crazy, that I'm working in an industry that is this much polluting. And to give you an idea about the extent of this pollution, the whole transportation industry today, you know, I mean, jet engines, you know, ships, tankers, lorries, trucks, trains, all of that today is using 30% of the global energy, right? So IT industry from 4% today in 7 years is going to be 20%. So it's a significant number. So I started to think that, okay, as somebody who's working in this industry, do I have any way to reduce the amount of CO2 emissions? So I started to look around. I found some articles that were interesting. There's one that is talking about that what programming language, how much emissions each different programming languages have, which is interesting, but it's again not telling you much about what kind of applications, what kind of platforms you should use and what kind of platform you shouldn't. So I started to hypothesize that if I can improve the efficiency of my applications, right, I should be able to reduce the amount of emissions. And I started to do a research to find out that if I can make any, you know, relation between efficiency and amount of emissions. And the result of that was this framework that I created that you can estimate the amount of CO2 emissions that a software platform generates. It is published in IEEE journal. It was published a few weeks ago, actually. So you can download the white paper. You can read it and find out that what the framework actually suggests. In these flyers that you have, there's a QR code. You can scan that, and you can download the white paper from there. It's free to download. So I'm not going to go through all of the details of the framework, but the idea is this, that I say that, okay, I want to estimate the amount of resources required by technology to handle a specific workload, right? So I say, for example, I want to store 100 terabytes of data on Aerospike. How much resources do I need, right? So that's simple. I can, you know, as an Aerospike expert, I can come up with the amount of resources required for that. And then there are some public data sets that good people of internet put together that are telling you that how much emissions the manufacturing of those resources produced, right? These are public information. You can find the detail in the paper as well. If you're interested, you can come talk to me as well. I can give you more detail about that. They basically found out that how much emissions producing a chip produces, how much emissions, what happened? No, still. So yeah, how much emission each different component, how much emission was produced for producing these components. And then there are some other data sets that are telling you how much energy these components use, and then based on where this data center is located and how much emissions energy production in that country generate, how much emissions that they generate, you can come up with the amount of emissions that the energy usage of those resources produces, right? And then you sum them up together, and you can find the, an estimation for the amount of emission that a software platform generates. So that was the topic of the paper, but okay, this is all theory, so I needed to put it in practice. So if this works, so yeah. So I did that. I basically used this framework for Aerospike for handling a petabyte of data. So that, okay, if I want to put a petabyte of data on Aerospike, how much resources do I need? And I did all of the calculations, and I ended up with 110 tons of CO2 emissions per year, per petabyte of data. All right? So significant number, but I needed something else to compare it with. And I thought that, okay, I need to have a nominally similar technology. And as I'm a Cassandra expert, I did that with Cassandra. I did the same calculation with Cassandra, and the number was 670 tons of emissions, CO2 emissions. And, you know, to be honest, this shouldn't be really surprising. I expected that to be like this because I already told you that, you know, Aerospike works with 5 times fewer resources than Cassandra. So I was like, okay, that's good. So it looks like that by moving from Aerospike to moving from Cassandra to Aerospike, you can save around 500 tons of CO2 emissions. But more importantly, I kind of proved that by increasing efficiency, right, I can improve the speed, I can improve the throughput, I can reduce the amount of resources that I use, which reduce the cost of my infrastructure, but I also can reduce the emissions as well. So this is not, you know, only Aerospike. You can use this framework for any type of application that you're using. This is just an example. And, you know, if you are, all of these calculations that are done on, are on Ireland, right? I use the Ireland numbers for the amount of emissions that are producing. If you're running it, let's say in Frankfurt, you can do the calculations for Frankfurt and you're gonna get the same numbers. But as long as you are comparing things to each other, right, it's the comparison, the ratio should be the same. You know, for example, if you move to Bahrain, the amount of emissions that Bahrain produces is 3 times than Ireland. So these numbers are going to be significantly larger. But you know, as Ireland is one of the popular data centers here in UK, I used Ireland. So that was the goal that I had, to prove that, okay, by increasing efficiency of my software, I can reduce the emissions. But there was also this question that if this 500 tons of emissions, is it something significant? Do we need to care about that? Can I, come on. Can I go ahead and say that Cassandra is killing polar bears? Well, of course not. You know, 500 tons is a lot, but it's not that significant. But to give you an idea how much 500 tons of CO2 emissions is, 50 hectares of trees absorb 500 tons of CO2 every year, right? So this 500 tons that you can save is like planting 50 hectares of trees. That's significant, right? And then remember this as well, that the size of the data doubles every few years. Some people say 2 years, some people say 5 years. Doesn't matter, it's exponential. So the savings that you're gonna have on your CO2 emissions is going to be exponential as well. If this is not good enough, I have another example. The estimated amount of data in the world is 100 zettabytes. It's 100 million petabytes, right? Not all of this data in databases, of course, right? Most of this data actually is not in databases. Let's assume 0.1% of this data is in databases. That would be 100,000 tons, sorry, 100,000s of petabytes, not thousands of, 100,000 petabytes of data. If we can save that much CO2 emissions, it would be equal to 50,000 square kilometers of land planted on trees. That's, please, that's equivalent to the surface area of Wales and Belgium combined, right? So that's a significant number. And I just have one last word. If you think that mankind has to reduce the amount of CO2 emissions that we produce, it is not somebody else's job to do it for you. we are responsible as well. So thank you very much, and you can download the white paper from here, and you can find us in booth 332. Thank you.